Hello everyone, so I wanted to go over the Zener Diode question from homework 3. So let's take a look. So using figure 9a as a reference, and I modified the figure, 24 volt DC is applied to a 6 volt Zener diode through a 100 ohm resistor to a load. There you go. Neglecting any load impedance, find the maximum current and power that can be provided to the load. And I added this piece of information to the problem. Initially, it was not there, but I felt that this was needed. So there's an older version of the homework where this statement is not there, and now there's a newer version of the homework where this statement is in fact here. So it says assume the current of the Zener diode is 3 milliamps. I'll solve it first for the new version, and then I'll show you the older version, basically what happens in the previous version where this information was not given. So, okay, so the first thing that you should do, and this is the same for both old version and new version, first thing is to find out, you need to know the current in the circuit, specifically the current that's coming out of the source. So the first thing to do is to do KVL here in this loop over here. Current goes into the plus, comes out the minus for the resistor, and here we can put, the way I teach it in my lectures, I put the little man, and he walks around the circuit in the direction of the current, and I say the algebraic sum of all the voltages in the closed loop is 0. That's Kirchhoff voltage law, right? The algebraic sum of all the voltages in the closed loop is 0. So as the little man walks around the circuit, you write down the voltage, but you have to note the first sign that you encounter. So as he's walking, right, the first voltage that you encounter is the source voltage, which is 24 volts, and the first sign you see is minus, so you write down minus 24 volts. And then he continues. The next voltage is the voltage that drops across the resistor. So this hasn't been labeled already, so we can name it whatever we want. I'll call it V sub R just for reference. So that voltage, the first sign you see is a plus, and the voltage is V sub R. Then the next voltage is the Zener diode. So they give us that the voltage across the Zener diode is 6 volts, and of course the first sign that we encounter is plus, so it's plus 6 volts. So you can solve now for the voltage drop across the resistor just by using Kirchhoff KVL, right? We have this and this, so we can just solve for VR and do a little bit of algebra, and we find VR, right? So basically VR turns out to be 18 volts. That's going to be a very useful piece of information to help us solve this problem. Before I go on, I just want to say a couple things about the Zener diode. So a Zener diode is a special type of diode that is actually designed to work in the reverse bias orientation. Normally, diodes will only conduct in the forward bias. In other words, you have the plus minus like this. Okay, that's normally how a diode works. But the Zener, as I said, is designed to work in the reverse bias. And what's unique about the Zener diode is that in the reverse bias orientation, it actually provides a nearly constant voltage. Basically, you can consider it to be a constant voltage. The current through it could change. You have some variation, but the voltage output will be the constant basically, and it can be designed to be any voltage really that you want for your particular circuit. In this case, it's going to be 6 volts. So in a way, it kind of works as a voltage regulator, the Zener diode. So basically, what's happening is that you can consider this 6 volts to be constant. Okay. So now that we have the voltage across the resistor, we can find the current through the resistor, right? We know the resistance, we know the voltage, we use Ohm's law, and we get the current through the resistor. So I is basically going to be V sub R over the resistance. That R looks really not good, okay? Here's VR, so we have 18 volts divided by 100 ohms. So we should get 0.18 amps. Now this is a series circuit, right? So the current in this resistor is the same as coming out of the source. So now what we're going to do is we're going to calculate the total power from the source. Okay. So I wanted to add something here. Let's call it P total source. Okay. So we have the source voltage and we have the current coming out of the source, right? So we can find the total power. So P total is just voltage times current. Okay, so voltage times current. So the voltage I'm talking about is the source voltage, and then the current is 0.18 amps. So the total power should be 4.32 watts. Now, another thing that we can calculate right away is the power that's dissipated or the power that's consumed by the resistor. There are a couple ways to do it. You can do I squared R, or you could do V squared over R, or you could do V times I because you have the voltage and you have the current. It really doesn't matter which one you do. For the sake of variety, I did it V squared over R. So basically, we're going to have the voltage across the resistor squared over the resistance itself. So basically, we're going to get here 18 volts squared over the resistance, which is 100 ohms. So the power dissipated in the resistor should turn out to be 3.24 watts. Now, this information about the Zener diode with the current being 3 milliamps is very important now. So now we can actually calculate the power that is consumed, so to speak, by the Zener. We know that 6 volts is dropping across it, and we know that the current through it is 3 milliamps, so P is V times I, right? So we can actually find power that's dissipated in the Zener. So that's going to be, I'll call it V Zener, I Zener. So V Zener, 6 volts, I Zener, they give us 3 milliamps. This minus, okay. So this will turn out to be 0.018 watts. So this is your total power. Some of it is going to be consumed here in the resistor. Some of it is going to be consumed in the Zener, right? So if I take my total power and subtract what's consumed here and what's consumed in the Zener, I get the power that must be consumed by the load, right? Energy has to be conserved, so that's why that works. So basically, we get our P total, right, is going to be P that's dissipated in the resistor plus P that's dissipated in the Zener plus P that's dissipated in the load. I can just use some algebra and solve for P load, which is P total minus P resistor, okay, P resistor minus P Zener. So P total is the 4.32 watts. The resistor is 3.24 watts. And then the Zener is 0.018 watts. So your P load must be, right, 1.062 watts. Now that we know the power in the load, we can find the current, right? How do we do that? So I'll add here and current through the load. Well, we know the voltage drop across the load, right? How do we know it? Because it's connected in parallel to the Zener. So if it's connected in parallel to the Zener, that means that it shares the same voltage as the Zener. So it's going to be 6 volts across the load. I also just found the power, right, dissipated in the load. So I can do P equals VI, right, and then I solve for I. So P load is basically V load times I load. right? And then I can just solve for I load. So I load is basically P load over V load. So P load is 1.062 watts, and V load is 6 volts. So basically, we find that it should be 0.177 amps. Okay, and let's just double check that. So I have here 1.062. Let me just make sure I have the right numbers here. 1.062 watts divided by 6, and yeah, 0.177 amps. And there you go. So that's your current through the load. Another way that you could have done this, instead of using the power, right, what you could have done is, we know the current through the Zener is 3 milliamps, right? This is KCL, or Kirchhoff's current law. I know my total current, which was 0.18 amps. I know here is going to be 3 milliamps, so then here I can find I load, right, by Kirchhoff current law, because the sum of the algebraic sum of the currents entering and exiting the node should be 0, right? So you can do check Kirchhoff current law. And this is a good way to check your answer. Right? KCL states algebraic sum of all the currents entering or exiting a node is 0. Okay? The way I do it is whatever currents, and this is the node in question, right? So maybe I guess I'll call it purple. So purple node here. Whatever current enters the node is positive, right? So I guess I'll call that the current, this one, right? We'll call it just IR, I guess. Did we call it IR before? We just call it I, so I. So it's plus I. Then any current that exits the node is negative, right? So this would be I Zener, and then I load are both coming out of the node, so they both are minus. So basically we would have here minus I Zener minus I load. This looks like a U in here. Let me fix that. So now we can just solve for I load, right? So I load is basically your total current, I minus I Zener. So I, right, the total was 0.18 amps. I Zener is 3 milliamps. I'm sorry, I already did the milli. So just like this. Okay? And then you're going to get the same answer. So it all works out. Now I want to just note, in the older version of the homework, right, if we do the older version of the homework, so I'm just going to grab this, make sure I grab everything. So grab the whole thing like this. And you know what? Let me just, I'll copy the whole thing. So let's just copy this. And you'll see in a minute what I'm doing. So paste. Okay. In the older version, this wasn't there. So you weren't given any information about the Zener except the voltage across the Zener. So the way you solve the problem is exactly the same. The only difference is that without any information about the Zener, we can't find the power that's dissipated in the Zener. So in the original version of the problem, it was assumed that you can assume lossless, right? So we basically would remove this part, and you would say in the older version we would assume P Zener is 0 because we weren't given any information, lossless. Okay, obviously that's not it's not realistic, right? Obviously you're going to have power loss in the Zener, but let's just say, you know, for rough calculation, we assume the Zener is lossless. If we assume the Zener is lossless, then this basically PZ is negligible, right? So we can, it's just 0 watts, right? So basically this part goes away, right? We don't even have this. Actually, I shouldn't even write. I should just have like this, right? The Zener is not even existing there. And maybe if you want, for the sake of keeping things, I can just put here 0 watts. Okay, we assume lossless. What's going to happen to the power? The power obviously is going to go, the power dissipated in the load is going to go up. You're going to get like 1.08 watts. All right. And then here, this is also going to change, right? Because now your load power has changed. So maybe you guys take a guess. What do you think is going to happen to the current, right? The current should go up, and it does. It'll go up to 0.18 amps. And of course, you can also check, you can check your, actually in this case, you couldn't check KCL because you were not given information about the Zener current. So basically, this is all you have. So if you take a look, 0.18 amps versus 0.177 amps, it's really close. So actually, the assumption that the Zener is lossless is not a bad assumption in this particular problem. Okay, it's a reasonable assumption to make your calculation a little bit easier. But if you wanted a really exact calculation, you do have to consider the power loss in the Zener. And that's how you solve this question.